All right, super. So thank you all for coming. We've got Jasmine Brewer here to speak with us today. So Jasmine got her undergraduate degree from UC or University of Colorado Boulder, her PhD from MIT, and then went straight to CERN as a postdoc. This is very rare. CERN only very rarely takes people for their first postdoc. It's a real sign of Jasmine's independence and maturity as a researcher that they chose to take her on the first shot. Jasmine is looking for a position, postdoc or faculty coming up. We wish her the best of luck. And we're very excited to hear this talk about jets and proton-proton and heavy ion collisions. Thank you very much, and please take it away.
Awesome. Thank you very much, Will, for inviting me to speak here. So today I'm going to be trying to give kind of hopefully an introductory talk on sort of jets and proton-proton and heavy ion collisions, and it's kind of related to some of my research, which I'll go into in a little bit more detail next week. As Will said before, please do feel free to ask questions during the talk, and this is much more fun for both me and presumably also for you if you understand what I'm talking about. Cool. But that did not work. So on a very basic level, what I'm working on and what I'm going to talk about today are high energy particle collisions, for example, like happen at the Large Hadron Collider here at CERN. And so at the Large Hadron Collider, what they do is essentially to accelerate to close to the speed of light hadrons, for example, protons, and then collide these protons in a detector and then observe all of the particles that come out and try to use those particles to kind of infer about what happened in the collision. And so most of the time at the Large Hadron Collider, what they're accelerating and then subsequently colliding, as I said, are protons. And so you can see a picture here of a proton-proton collision where the protons are coming in along the axis of the cylinder, and then they collide at extremely high energies and they produce a bunch of particles. And those are shown by these kind of orange and green tracks, which come out to the detector. And then so that by studying sort of the correlations and the structure of these particles, we try to learn about what happened in this sort of first interaction. And the way that a proton-proton collision produces particles is kind of what I'm going to try to address first in actually most of the talk today. But what I actually work on is a slightly more kind of complicated system where instead of colliding protons, you're actually colliding large nuclei. For example, at the LHC, they collide lead. And for this purpose, you can kind of roughly think of a lead ion as just like a big bag of protons. So a lot of the types of things which happened in proton-proton collisions also happen in heavy ion collisions, except that you have interactions between enormous numbers of protons because these nuclei are so big. And so the sort of energy density, or like the number of particles which are produced in heavy ion collisions is enormous compared to proton-proton collisions. And because of that, there's also a lot of interest kind of dedicated to study heavy ion collisions. And so kind of in the end of this talk, and then also in the talk next time, I'll be talking sort of more particularly about heavy ion collisions. But since these are kind of more complicated, again, I'll first start talking about proton-proton collisions. So basically what happens, so here, as I was saying at the LHC, then you, in this big ring, you accelerate protons and collide them together. And kind of the basic, sort of the first thing that you need to know, I guess, about protons is that they contain quarks and gluons. And so when we talk about proton-proton collisions, in practice, I'll actually be talking about interactions between quarks and gluons, which came out of each of these individual protons. And so to kind of understand what I'm going to talk about in the language I'm going to kind of use, I want to just walk you through understanding these kind of diagrams, which we draw to understand this interaction. So here, you should really read, so this diagram is encoding sort of an interaction between gluons and two protons, which produces gluons. And so the way that you should really read this is on the left, you have the particles which you had initially. So in this case, you get one gluon from this proton, for example, and one gluon from the other proton, and they interact in some way, which is kind of this intermediate state, and then they produce stuff. And that's these, in this case, these two gluons, which are in the final state. And so then I'm going to be studying basically these products of a proton-proton collision, which are these like final state gluons. So just to kind of reiterate, this diagram is sort of a concise way to say, okay, you got one gluon from each of the protons, they scattered in some way, and you have two gluons also in the final state. But you can also have other types of interactions which can happen between gluons. So this is just one other example where you have one gluon coming out of each of the protons. They interact in some way, and then at the end you have quarks. So that's what these straight lines are as quarks, and the curly ones are gluons. So this is kind of the basic of understanding the rest of the talk. So if you have any questions at this point, please interrupt me and ask, because I may not have explained it well. All right, cool. Perfect. So as I said, the idea is that protons contain quarks and gluons. And what I mean by this can actually kind of be quantified in essentially a probability distribution for finding a quark or a gluon in the proton as a function of essentially the fraction of the proton momentum, which is carried by that quark or gluon. So, you know, I won't explain to you all of the curves, but two of the most common types of quarks are the up and the down quarks. So what these curves are telling you is that there's a relatively high probability of getting up or down quarks, which have a pretty large fraction of the proton momentum, like 20% of the proton momentum, 10%, 20%. But on the other hand, if you go to like smaller fractions of the proton momentum, there's really an enormous number of gluons in the proton. So this is actually the gluon distribution over 10. So there's a huge probability of getting gluons out of the proton. So that's kind of why I've been giving it as an example the case that this initial state is two gluons, because that's a really common configuration that you can get when you scatter two protons together, is that you're really basically having an interaction between a gluon in one proton and a gluon in the other proton. But then once you kind of know sort of what partons you're actually getting out of the proton, whether you're getting gluons or quarks, then it's really these interactions in QCD which determine what kind of final states that you can have coming from those initial states which you got out of the proton. So these are some examples of the way that you can produce sort of the permutations, I guess, that you can have of like stuff you have out of the proton and stuff that you get in the final state. So you can get two gluons out of the proton and produce two gluons. Whoa, sorry. You can get two gluons out of the proton and produce two quarks. And these are the two processes that I talked about on the last slide. But you can also have other stuff. You can get two quarks out of the proton and produce two gluons. You can get a gluon out of one proton and a quark out of the other proton and produce a gluon and a quark. So you can get kind of all of these kinds of different sort of interactions between different types of partons just from scattering two protons together. And that's because they're kind of these rich objects which are containing a lot of different kind of quarks and gluons. Okay, I don't see any questions so far, but again, please stop me if you have any questions. So essentially now we've collided two protons and we've produced partons. So we've produced either quarks or gluons, which are now kind of going back to back. You know, if you think about the frame where like the protons came in and collided, Then now we don't have protons anymore. They went somewhere else, but we have like, say in this example, we have two gluons going back to each other. And so then is kind of the question, like what happens next? And sort of the technical details of why this happens, maybe I won't go into in too much detail, but basically these gluons, which are going back to back, are super energetic. They're very off mass shells, so have very high virtuality. And on technical ground, maybe it's not important exactly what that means, but the point is, in terms of what happens, is that this means that they sort of want to successively radiate more and more gluons. So like a gluon in this state isn't sort of stable. It just doesn't just stay a gluon, but it radiates a lot of stuff successively. And these sort of radiations are also determined by sort of QCD processes. So the idea is that, you know, if you have one parton, say a gluon, for example, then there's a probability which you can kind of compute in QCD for that gluon to split to two other partons, for example, to two more gluons. And that sort of probability is determined both sort of by the angle between that splitting and also by the momentum sharing fraction, which here I'm calling Z. So essentially the probability for a splitting to happen depends on kind of the kinematics of this splitting. And so from that, you can kind of compute, given that I have a gluon, what is the probability that, you know, that I will have two gluons or successively more emissions as a function of the structure. And so what this kind of means in practice is that if you iterate these kind of splitting probabilities, then you end up just having sort of a cascade of splittings off of this initial gluon. So each of these, this gluon kind of goes along, and then it'll sort of split into two gluons with this probability. And then maybe one of those gluons splits into two more gluons, and you just have kind of this cascade of QCD splittings until they sort of reach a non-perturbative scale in QCD where they turn into hadrons. So the idea is kind of that all through this intermediate regime, you're sort of successively splitting all of these hadrons, or all of these partons, which then eventually will turn into this kind of spray of hadrons. And it's this sort of full object, which we call a jet. And I'll try to sort of motivate, I guess, in the coming slides, like why this object is interesting and why we want to study it, both sort of in proton-proton collisions and then later in heavy ion collisions. So just to kind of say that again, what this whole process that I've just described looks like in a detector, which this is kind of a picture of the detector kind of in the plane perpendicular to the direction where the protons collided, is that you get these, say, gluons back to back, and each of them kind of showers down in all of this radiation until you get these kind of two piles of radiation back to back from each other. And these piles of radiation we call jets. Does that make sense so far? Are there any questions like from students or anything? Okay.
Maybe can I ask a bit of a technical question, which might be a bit unfair at this stage, but this Pij of Z, what's its normalization? Because aren't there, you know, it blows up and it's not quite a probability, or am I misremembering?
Yeah. So I shouldn't have really, I changed this from a previous slide where I said like splitting function and changed it to probability. So yeah, strictly speaking, you shouldn't really interpret this directly as a probability, because if you have like very soft radiation or something like this, then these so if Z is very small, then this function for some of these splitting functions can blow up. And therefore, yeah, you should really maybe treat this more delicately than I am doing it in this talk. If you work backwards from sort of hadron level, I guess, if you look at these hadrons and then you try to understand what's happening kind of working backwards in the shower, then in some way these problems are kind of solved, I would say, or at least you have some definition of what kind of the splitting functions mean in terms of kind of quantities which you can measure. But yeah, I don't know if I should go more into detail on that or not. Kind of depends what you want. But
I guess so. Yeah. So first of all, I'm sorry. I wasn't trying to play gotcha. It was really a genuine question because, like, it's always, the picture is always where you have 1 goes to 2. And then how do I think about that as either a probability or not? I mean, I'm used to, in the jet physics case, we talk about probabilities of emission for single inclusive distributions. And so then the idea of a fixed number no longer applies. So you have this idea that you emit multiple, say, gluons. So these pictures that you show here are always what's shown, and I guess is your point that I should take the pictures with a grain of salt, or is it really that I'm going 1 to 2 to 3 to so on and so forth?
Mm-hmm. Yeah, I see what you're saying. So
maybe it's the point that this is a quantum process, and so like I don't actually know what's happening in the middle. I can only ask questions about observables at the end.
So that is definitely true, and something that so what is definitely true about this picture is that it is only a picture, and there are a lot of kind of subtleties in this implementation, which I think do have in large part to do with this kind of issue that you're describing. So like, for example, if you, what are these kind of things? So if you want to really like, I think concretely implement the splitting functions in kind of the correct way, then there are, I'm trying to remember all of the like kind of details of this, but I think there are a lot of complications in like how you keep track of like momentum flow, for example, between like, you don't really have that all of these splittings are like fully independent of each other. And so in this picture, we're kind of writing like that you just have a splitting and then you have another splitting and then you have another splitting. But that's kind of formally not correct. And there's sort of interaction. I shouldn't say interactions because the particles are not interacting, but there's kind of correlations between the momenta and different processes that doesn't allow you to kind of just treat them fully independently. And I'm certainly not like an expert on parton showers in vacuum, but like these objects kind of themselves are studied extensively in, and there's a lot of work on improving the QCD accuracy of these objects. And in that way, these kind of parton shower, as I'm drawing it here with just these like successive splittings, is really just a picture which doesn't hold weight by itself. So you shouldn't go into, these parton showers can be shown to be, for example, leading log accurate or whatever you want to say at the level of hadrons. So at the kind of level of things which you can actually observe, but they make no guarantee about the correctness of this picture. So if you dig into Pythia or something, one of these Monte Carlo generators, and ask about the, this particular splitting in the shower, like Pythia can tell you what it thought the answer was. But there are all sorts of like momentum redistribution and stuff like that, which happens in the parton shower between these like two different legs, just to like maintain momentum conservation, for example, in the shower. And so you really shouldn't look at this, you really shouldn't look at this splitting by itself in a parton shower and hope that it makes sense. At least not to like some fixed accuracy in QCD. Then you should only look at these hadrons formally.
Super, thank you. That actually is really nice.
Any other questions? All right. Cool. So just to kind of recap a little bit what I was saying, and I'll try to kind of keep track of time, because we can always finish the next one. So okay. So what I was kind of saying is that you have these back-to-back gluons or quarks or whatever, which you got out of this interaction between the protons, and these are back-to-back, and then they're kind of successively radiating through these QCD splittings. So you end up with a lot more than one gluon. You might have 5 or 10 or whatever different partons, which turn into these kind of collimated sprays of hadrons when you look in a detector, for example, at the LHC. And these kind of collimated objects, we call them jets. And so that's kind of the focus, I guess, or part of the title of my talk. So I want to kind of tell you about why these objects are interesting. So kind of one of the main points, I guess, of why we want to sort of study all of this radiation as an object is that we really want to try to access the kinematics of these gluons, for example, which came out of the interaction between the proton. And so kind of the basic idea is that if we manage to collect all of the radiation, so in this kind of picture of the parton shower, where you have all of these successive splittings, because of like momentum conservation, for example, you know that if you manage to actually find all of the radiation which came off of the splitting, so if you manage to get all of these partons together and you sum up their momentum, you should get the momentum of this initiating parton, for example. And momentum is not the only feature like that. There's also, for example, like the invariant mass, which if you've taken special relativity, you probably also know about. So there's a lot of kind of features of this initial parton, which we can't access from any individual one of these partons, but we can access if we manage to collect all of them together. And so kind of the basic idea of jets, like of accessing them all together, is that we want to try to access this information. So we want to know, what is the momentum, what is the invariant mass, stuff like that, of this initiating parton. And so to do that, we basically, at least in the simplest case, we essentially have a cone, and you try to find, where all of the energy fits in the cone. So, maybe you just draw a cone around all of these radiations, and you count up the momentum, and then from that, you get something which is a pretty good proxy for the initial momentum, for example, of this parton. Yeah.
What about the charge? What do you expect to get when you measure the charge of the jet?
Yeah, that's a very good question. So people are quite interested in, so the charge of the jet is an observable, which people do measure. What's a little bit complicated is that, so here you have, quarks and gluons and stuff. But what will actually end up in the jet is just hadrons. And so you don't kind of get direct access. So you can count up like the electric charge, for example, of hadrons in the jet. But it's kind of delicate to use that, like, because sort of hadronization process is kind of, I guess, unclear exactly how it happens and doesn't necessarily maintain sort of the charge of all of these partons in the jet. What you actually get for the jet charge is not, it's still kind of a distribution. So you don't necessarily access the, like you would like to say, oh, okay, by measuring the jet charge, we can access the electric charge, for example, of like, you know, was this a quark or a gluon or something like that? But it's not so straightforward. And as far as I understand, basically the issue is hadronization.
But that's actually just a briefly follow up. That's a great question, right? Because suppose you have the QQ bar in the final state, and it starts out with a third of a charge. Yeah.
Look, this actually goes even deeper. When you make this nice, beautiful back-to-back thing, right? And you have no colored radiation in between, right? Normally, if you have two colored particles produced that each carry away, say, make two gluons, right? If they're kinematically connected in any way, you would fill up the kinematic region in between. There's lots and lots of stuff because you just spread color across this and this and that, this and hadronides. If I look at these jet pictures, it always puzzles me that you can initiate this with a gluon pair, each being in the adjoint, right? And you have no color spread over the rest of it, right? You see sprays going in opposite directions, and there's nothing to fill up phase space in between. So that there is something, there must be some very, very extremely soft color transfer happening for this to, but in a directed way, and that's what I don't understand, honestly. Really, because soft is usually not directed, soft is going anywhere.
What's amazing is somehow factorization saves you, right? Like that somehow you don't have communication between the initial state, the final state, and the hard scattering of it.
So I don't know if people have better insight into this by now, but I'm always puzzled by this.
Yeah, it's a quite interesting question. Maybe Will has more to say about it than I have. Like, maybe not. But I know people do talk about like the influence of like color connection between, like, for example, in principle, if you had two gluons going back to back, or you have a QQ bar pair going back to back, or you have some other process, then these in principle have different color connection to the event. So like, you know, a gluon produced in association with a gluon, then like you wouldn't have sort of, because the picture that we kind of typically have, even like, you know, in some of my own work, is that like a gluon jet is kind of a gluon jet. It doesn't matter what was produced on the other side. And this is a very common picture, which actually I would say works pretty well in phenomenology. But I think for exactly the reason you're saying, it's maybe not obvious, at least to me, exactly why should that work? Like, why are these color connections not important between, but I don't have anything insightful to say.
I have not, you're not the only one.
I also see a question.
Yeah, is the sort of the difficulty in measuring something like, or inferring charge of the initial parton from the charges of the final hadron, is that a result of us not theoretically what happens in hadronization, or is that more of an experimental limit in that we can't discriminate like other particles in this code from things that came from the jet?
So I think.
Okay, so sorry, please continue.
No, sorry, I just didn't catch what you said.
No, I said you have to add up integers and get a fraction. That's what.
Yeah, I think So basically the essential issue is that in order to produce hadrons, okay, so people don't know how hadronization works, so I'm not going to tell you like how we produce hadrons because I shouldn't pretend that I have any idea. But at least what's kind of imagined is that, okay, you need to get like some quarks or gluons or stuff like this produced from the vacuum in order to kind of have them combine into hadrons. So like, sorry, I don't know your name, who was just speaking on my left. But as he was saying, if you add up the electric charges of all of these partons, which are here, basically, in order to produce these hadrons, like these have like some funny fractional charges. And so these hadrons have all integer charges. And so somehow you have to get between the two. And the way that happens is probably to get some QQ bar pairs and gluons and all of this stuff out of the vacuum and have them kind of combine into hadrons, which have to provide that electric charge. So I would say, to me at least, it's a theoretical issue, which is that somehow these partons which have fractional charges have to become objects which have integer charges, and the way that they do that is not understood, and you therefore can't really like access, I guess, reliably the charge of these kind of partons, or it's almost not like well defined, I guess.
All right, thank you.
Any other questions? Cool. Yeah.
Well, there's one more. Yeah, go ahead.
Yes, go ahead.
Maybe a much simpler question. The solid angle of the cone here, is that completely determined by the initial momentum?
Is that, sorry, is that what by the initial event?
So the momentum of the gluon that initiates the shower, does that completely determine the solid angle of the cone you get?
That's a very good question. So in practice, like in experiments, for example, they just fix the size of this cone to be a particular radius. So like 0.4, that's just how big the cone is. But your question is extremely relevant because the features of this gluon and how this radiation pattern happens determines how big the cone should be. And so if the cone that you've kind of picked for experimental purposes is too small for what it should be given the kinematics of this hard process, then you're going to miss out stuff. So I kind of tried to like qualitatively sketch that here, that you're not guaranteed to get everything that you wanted to get. And there can be kind of systematic ways that you lose stuff exactly through what you're talking about, that like some processes, if you have like a wider angle of this like first splitting or whatever, then you're kind of systematically underestimating kind of the kinematics of that hard process by doing this procedure. So, I mean, of course, they study this and they try to pick a cone which is wide enough, and they try to understand like what are the like problems associated with that. But it's an extremely relevant question, and like a lot of what I'm going to say does kind of at least rely to some degree on the idea that you got most of what you were like hoping to get. And if you miss a lot of it, then you're missing some of the important kind of physics. Yeah, so very good question.
The need to fix this experimentally fix the radius of the cone, is that just in order to detect these, or why is it necessary to a priori fix the radius?
Yeah, that's a good question. So for sure it's convenient, because then you can kind of, what they get in practice then is just like a bunch of energy deposits in the detector, and they want to like go through all of these events really fast. And of course you can kind of imagine, the easiest thing is to just like slide a cone around and like see how much energy ends up in that cone. So I think why it's convenient is obvious. In principle, you could try to do something else. Like even in this picture, you see that this jet really needs a larger cone than this one does. And I'm sure that you could try to kind of dynamically resize this cone. I'm guessing it comes with huge experimental problems, so I wouldn't be surprised at all if the issue is basically just trying to estimate systematic uncertainties of this. Would be very difficult. Also, of course, this is like a particularly like cute picture where you really just have like two jets. Of course, you could also have like, another bunch of radiation here, or like some random stuff, or when I talk about heavy ions later, then there's just like an enormous amount of stuff everywhere. So this is clearly like a portable definition. I think you could do better, but in practice, like you might run into kind of roadblocks making a good definition. And this happens to be something which you can calculate, you can measure pretty easily, and people just try to kind of work within that. But I think it's a very good point and an interesting possibility as well.
There are also issues in defining jet observables that you can define these things and always essentially measure anything you define, but you cannot always calculate things reliably. And there's this issue with infrared safety of jet observables. So there are things that you cannot calculate in perturbation theory of any level of sophistication because the quantities are sensitive to long distance physics. And if that happens, forget about calculating anything. And then, despite the fact you can always measure this because nature knows how to fix this, you don't know how to calculate it. So you have no test of theory, right?
Yeah, also
Sorry,
very good.
sorry for interrupting you. This is one of the things that these guys maybe should know.
No, perfect. Any other questions? Good. All right. Yeah, so maybe I'll just try to recap also for myself. What I was saying is that, okay.
We went all the way in.
Here in these jets, we try to collect all of the information which came from this hard scattering. But actually it turns out that we can kind of, in some way, we can use jets to sort of access also more detailed information about sort of the structure of this shower. And so that's what I want to kind of talk about next, is how you can kind of look inside of the jet, and how the distributions of partons inside of the jet also provides information about the splitting. So here I was kind of drawing this picture earlier where we have these splitting probabilities for sort of the angle between these emissions and their momentum sharing fraction. And then through these successive splittings, we're building up this shower, which then turns into a jet. And the point is that, like, to some extent, how these particles are actually distributed inside of the jet also tells us even more information than just about the first sort of this initiating gluon. And the point is kind of that this sort of splitting here, this first one, in some ways kind of the most energetic or the widest angle. And I'll go into like a little bit more detail, like what I mean by that later. But what you can kind of imagine here is that, like, when you have this kind of structure, then over here in this area, you have like a fair amount of energy. In general, you actually have all of the energy which was on this parton, this gluon. And over here, you somehow have all of the energy that was on this one. So in some way, even when you look into the jet, you can actually try to access kind of hadrons which came from this leg of the splitting, from hadrons that came from this leg of the splitting. And so the point kind of here is that, like, say that this splitting is kind of symmetric. So you get like, you have one very high energy gluon here, and then it splits into like two, both pretty high energy gluons, which then like keep radiating stuff. Then you would imagine that you have kind of what they sort of would call a two-pronged substructure of your jet, meaning that you have sort of one prong where you have a lot of energy kind of over here coming from this gluon, and you have another prong, which is a lot of energy over here coming from this other gluon. So this is a particular kind of way that the energy of the hadrons inside of the jet looks like, that tells you about what that kind of underlying splitting look like. On the other hand, if you imagine a case that this kind of splitting had like essentially all of the energy was carried off by this gluon, and this one was super low energy, then you could imagine that instead your jet will really have kind of only one prong. So essentially all of the energy is carried over here and is coming off of this branch. And since this one was like not very energetic at all, maybe all these hadrons over here are super low energy or whatever. So this is like a very qualitative picture, and there's some details here I'm skipping over, but the idea is that basically even once you've collected stuff in a jet, you can still get more information about how the splittings happened by looking at how the energy is distributed inside of that jet. And this has become a pretty big like sort of program to try to use this information about like correlations and stuff between the energy inside of a jet to really try to access features of these splittings. Does that kind of make sense? Do you have any questions at that point? I don't see any. Okay, so I'll just try to maybe like, wait. Okay, well, anyway, I put my slides in a different order than I expected, but that's okay. So I'll say kind of one thing, I guess, about what that means for phenomenology, which is that kind of depending on what this, so maybe to go back to these splitting probabilities. So here I wrote them kind of generically as like you have some parton I splitting to some other partons J and K. So these could be, you know, this could be a quark, this could be a gluon, these could be quarks, they could be gluons. So these are dependent on kind of the structure of these splitting probabilities for different QCD partons. And so these kind of probabilities are different depending on whether the splitting is a gluon splitting to gluons, or a gluon splitting to quarks, or a quark splitting to a quark and a gluon. These sort of splitting functions are different. And so what that means is that depending on what kind of parton you have, which is splitting, also the basic like features of this radiation also changes. So the point kind of is like, okay, if you have a gluon in this like initial state, and this is kind of the example that I've been showing the whole time, then most likely it splits to gluons. And the structure of that splitting is something particular. So this has like a kind of characteristic type of radiation pattern, which you'll get on average inside of the jet. But on the other hand, if you have a quark here on the, like if you have an initial quark initiating the jet, then this first splitting is almost always a quark splitting to a quark and a gluon. So this requires, I guess, some knowledge of QCD to understand exactly why I am telling you this. But if you just kind of take it as a given, essentially this first splitting is different depending on whether you have a gluon, in which case it's usually two gluons, or you have a quark, in which case it's a quark and a gluon. And the structure of these splittings is different. And so therefore, kind of the argument that I was trying to tell you on the last slide, which is that this substructure inside of jets cares about like exactly the kinematics of the splitting. It also kind of cares about whether that splitting was typically a like glue to glue splitting, for example, or a quark to a quark and a gluon. And so what this kind of ends up meaning in practice, for example, is that if you have a jet which comes from a quark, like this one, then it's typically narrower than if you have a jet that comes from a gluon, because this splitting is typically narrower. And so all of the energy kind of ends up in a smaller cone if it comes off of a quark in general than it does if it comes off of a gluon. And that's kind of a feature of these splittings which can happen in this kind of jet, if that sort of makes sense. So that's kind of cool in some way, because it gives us some way to try to access, you know, even though you can't access like the charge, for example, of this parton. And in general, it's quite hard to access sort of the flavor, like to tell whether this parton is a quark or a gluon on a jet by jet basis is either hard or possibly impossible. But at least on average, you actually can tell quite a bit about whether it's a quark or a gluon, because there's sort of different characteristic types of structure inside of jets, because they're formed from these different splittings. So that's actually pretty cool. I think that this kind of idea sort of gives us access, at least indirectly, to this parton flavor that generates the jet. Any questions? All right. So now I'll just kind of say something a little bit more formal, but I hope is kind of just puts on a little bit more quantitative of ground what I've already said. So the basic idea is that in QCD, emissions are ordered in angle. So the first emission, which happens in the shower, is at wide angles, and then all of the successive emissions afterwards happen at smaller angles relative to the emitter. So kind of subsequently, there's an ordering in the angle of emissions in the shower. And this is really powerful, actually, because what I was telling you so far is that you can kind of look at how energy is distributed inside of this cone to try to like tell kind of what happened in this splitting, like how wide of an angle was this initial splitting. But what's quite cool is that because of this angular ordering, actually you can just directly look at the hadrons in the jet, and this property means that you can essentially reverse back the evolution of those hadrons in the shower. So you can essentially take a jet, and again, like our friend pointed out, assuming that you manage to get everything inside of your jet cone, but if you manage to do that, then you can actually kind of what they call recluster, but essentially to trace back in what order all of those hadrons were emitted during the parton shower. So essentially the idea is that then you can associate kind of depending on the relative angles of the hadrons from each other, you can associate an emission history directly from the jet. So here I've been drawing a picture, which is like a parton shower and that turns into hadrons. But the idea of this technique is that you can also look at the hadrons and reconstruct an emission picture. And that relies on this particular property of QCD, which allows you to kind of tell in what order an emission happened based on the angles of the emission sort of with respect to each other. And this is maybe like a little bit technical, but the kind of point is that, you know, I've given you some picture about accessing this first splitting, but actually it ends up that you can actually access the kinematics of any splitting in the shower in this way, because you're able to kind of reconstruct the shower. Then you can take sort of, you know, if you say I'm interested in this splitting, which I have delineated by the black goes to green and pink, then this reconstruction that you were able to do tells you exactly which kind of energy you should sum up if you want to know the energy of this splittee. You should take and add up all of these green, all of the energy of these green prongs, because that was kind of the emission history. Whereas if you want to know the energy of the pink splitter, you should add up all of these other prongs. So this is a very powerful technique. And of course, there's caveats to this, especially in hadronization. But it's a quite powerful technique to try to access sort of the kinematics of any splitting in the shower sort of from the jet. I don't know if this was clear, so please do ask questions if you have any. Yeah, good.
But just curious about how this angular ordering actually, how it manages to persist through hadronization. Like, if we don't really understand how these partons can hadronize, how can we hope to even reconstruct that? It's quite amazing that it manages to work.
Yeah. So I think that's an extremely good point. So I think what it really relies on, and this is something which I guess is intuitive, although I don't know on how firm a footing it is, but at least has some intuition, is that hadronization doesn't move stuff a lot in phase space, sort of. So, you know, the charge, for example, can change a lot because you're pulling you're pulling stuff out of the vacuum in order to make this hadron, but it doesn't really change your momentum a lot because you're like, you're pulling out stuff which has quite like low momentum. And so you might have like a little bit of like kind of changes in the momentum, or like a little bit like, you know, you had a parton here and you have a hadron like a little bit, a little bit different place in phase space, but it doesn't kind of change you dramatically in phase space. And so we really kind of rely on that feature in order to sort of say, okay, the basic direction in momentum space of these particles isn't going to be changed much by hadronization. And so then you can kind of still take this, these angles are still like a pretty good proxy for the angles of the partons, even through hadronization, whereas something like the charge wouldn't have been. So it's kind of a particular property which you have to sort of assume, but also seems to work relatively well, at least for the hadronization models we have, of how you think that process happens, is that it's pretty local in phase space and doesn't move stuff a lot. Any other?
How far back can you trace this history?
So in principle, you can trace it all the way back to the initiating parton, as long as kind of, so I took this graphic from a different talk, but like, if you have sort of very wide angle or like very soft emissions or something like that, which is kind of either lost in your jet. So like if you have stuff which is not in your jet, then you can't use this kind of technique to trace back the parton shower. Also, if you want to so in principle, you can reconstruct the history of anything which is inside of the jet. It's quite common of a technique to kind of remove particularly wide angle and particularly soft radiation in order to try to access like hard splittings in the shower. So people are especially interested, I think, both in perturbative QCD, so like in PP, but also in heavy ions in kind of especially hard splittings. And so for that, you might also kind of try to systematically remove some of the radiation which doesn't satisfy that criterion, like which is particularly soft or particularly wide angle. But in principle, at least from this technique, you could reconstruct all of it as long as you found the hadrons.
When you're removing the soft stuff, that's the gluon, yes?
Yep. Exactly. All right. We're okay, all good? Yeah. Cool. So I was gonna actually say a little bit more stuff, but I think since I'm at the end, I will just kind of say the summary of this section, and then we can also just incorporate what I was going to say into the next talk. So it's kind of a nice stopping point, I think. So kind of what I tried to sort of motivate to you today is that we produce these objects called jets in proton-proton collisions from these like very high momentum transfer interactions between quarks and gluons in these incoming protons. We produce these sort of collimated sprays of hadrons in the detector, and we can really try to use these objects, which we call jets, in order to really reconstruct the kinematics of those interactions and try to understand kind of in more detail what happened in the collision. And then I think a very kind of important sort of aspect of this also for what I'm going to talk about next week is that kind of how these jets actually look and the correlations between particles sort of inside of jets can be quite different depending on what splittings happened. So by looking inside of jets, we also get more detailed information onto sort of not only like what was the kind of original parton which came out of this interaction between the protons, but also what happened sort of subsequently in the evolution of jets. And so I think these pieces of information together kind of make jets like a particularly interesting object in which you really kind of have a lot of handle on QCD in this regime. And so that's sort of why we're interested in it. And next time I'll talk a bit about well, jets and heavy ion collisions, which is sort of what I work on. And then if I get the chance, also a little bit about some of my ongoing work kind of related to this. So yeah, with that, well, thank you for your attention, and yeah.
Super. Thank you so much. I think we have a couple people running out just because of time.
Yeah. Sorry that I'm a couple minutes over.
No, not at all. I think that's wonderful. We had a lot of questions, and
we slowed you down tremendously.
Yeah. So wonderful to find a good stopping point. Of the people who remain, are there any maybe last questions for Jasmine before we release her back to CERN? Maybe I had a question, which was you mentioned there are some caveats for the angular ordering and being able to reconstruct the splitting evolution. Could you talk a little bit about those caveats?
Yeah, sure. So I think for proton-proton collisions, I think one of the most important caveats was already brought up by one of our audience members, which was that, of course, here you're looking at hadrons. And so you're sort of trying to reconstruct an emission history from the hadrons. And I think, okay, so that's one issue. So that's hadronization. I think another one kind of hinges on what you were bringing up at the very beginning, Will, which is like, what does this shower actually mean? And like, can you really dig into the details of this shower? And in some way, I think that that's actually what I find interesting about this like jet substructure techniques, is that it gives you a meaning for what the shower looks like from the hadron level. So while this is sort of fully a picture, which is kind of only a like Monte Carlo concept to some extent, once you get these hadrons, you can do this sort of reclustering, and you might get a slightly different, I mean, you probably do get a slightly different answer than Pythia would hand you to tell you what was exactly the kinematics of all of these splittings. But it's not totally obvious that, you know, I think you shouldn't really trust Pythia. So it's not obvious that the way that you should benchmark the correctness of this procedure is by comparing to Pythia. So it's kind of an interesting case where it's like, you know, you probably get something qualitatively similar to Pythia, but probably not exactly the same thing. But in some way, this gives you almost a way to define the parton, like what the parton shower looked like from hadron level, which I think is also pretty cool. So it's like, that's like half caveat and like half advantage, I would say. It's like the caveat is it might not exactly match this picture, but you probably shouldn't have trusted this picture anyway. So maybe, you know, maybe you should trust the more this kind of observable definition of the parton shower than kind of this model level version of the parton shower.
So what's actually being used here? You mentioned Pythia. What happened to Herwig in this game, for example? I mean, there used to be a number of codes out there that were doing certain things differently. Are they still competitive? Has this disappeared? Any comment?
Yeah, so I think that, okay, so I happen to run Pythia because I happen to know how to run Pythia and have it installed on my computer.
It's a good argument.
But I definitely know of people who use Herwig, and I think it is often kind of used, like, you know, if you have like two fundamentally different parton showers, you can also try to kind of gauge the sort of importance of the detailed modeling by comparing them. So I think it's also quite common still that like experimental papers, for example, will show both like Pythia and Herwig, for example, to try to gauge, like, I think it's Herwig, which has quite different hadronization to Pythia, if I remember correctly, although I forget the details, but like they have a number of kind of different aspects in the modeling. The only final thing I would say is that I think all of these parton showers, which are currently like publicly available, are also like, I think they're leading log accurate. And there's been a lot of work, actually a lot by the QCD group here at CERN, and some kind of collaborators of theirs to develop sort of like next to leading log accurate parton showers.
So you're telling me this has not been achieved yet? I mean, I know this is a heck of a problem, right? Because of interference and other little nastinesses in this game. Well,
so my understanding is that they have achieved it, but recently enough that there's not like a broad multi-purpose code, including all of the types of things which Pythia would have, which someone of like my level of competence could run. So I think that they're they're either private or they're like kind of public in a way that's not just sort of out of the box, like run me a proton-proton collision and tell me what is the answer. But they've made quite a lot of nice progress. So I hope that that will be coming soon.
Yeah, following up with that question, is the angular ordering a leading log statement?
I forget exactly the order, whether it's leading log or next to leading log, but it is accurate to some order in QCD, which is not exceedingly high. Yeah, that's actually that question I should know the answer to, and don't, whether it's leading log or next to leading log. But yeah, maybe I can ask one of my friends down the hallway and let you know over email.
Sounds great. Or next week.
Oh yeah, next week. Also that.
Or both, yeah. Super. Any last questions for Jasmine? Super. Well, thank you very much again for taking the time. We really, really appreciate it.
Yeah, thanks a lot. Thanks for the very nice discussions and everything. It was nice to chat with you guys.
We were just rushing into this too fast to actually introduce ourselves, right? So I'm Herbert and this is my one.
Hi, very nice to meet both of you.
I'm Andre. I'm a master's student.
Oh, very nice.
Yeah, my name is undergraduate.
Very nice. Nice
So
to meet you all.
Next time around, you will at least have a few names.
Yeah, it would be great to meet everyone, at least meet virtually.
Yeah, exactly. Cool. Well, thanks again, and let me turn off the recording.